So yesterday we were talking about oxidation reduction reactions, and we talked about that traditional definition of redox. Again, I really want to stress that traditional definition of redox is not incredibly important. There's a really, really tiny chance it'll show up on the diploma, so I really have to talk about it. I would focus much more on this idea of if we're losing electrons, that is oxidation, and if we're gaining electrons, that is reduction. Did you say Lior? What? Oh. There's, I think Hunting Hills. They say, like Rallyo the Ogre or something like that. It's this weird, I had never seen it before. People have talked about it before. I don't even know. Yeah, I don't even want to know about it. It's hunting. Yeah. French. Okay, so this is going to be really, really powerful for us. I would focus more on this, and the reason why we're going to focus more on that is because we're actually going to add some letters onto the end of this. Whoa. As we go through the unit.
More complicated.
Yeah, so we're going to add a C, and we're going to add an O, and we're going to add an A, and we're going to, we're going to say, Gurkoa. Yeah.
Let's go. I'm so excited. Can't you see my excitement?
Yeah, I can.
It's flowing from my face.
Yeah, your excitement is literally vomiting everywhere right now.
Exactly.
Yeah. Okay, listen up. So, what do you notice about Gur and Leo? What do you notice about them?
They both have E's.
They both have E's, so they both involve either the something of electrons or the something of electrons. Okay, but more specifically, when you compare this one to that one, they're opposites, right? One is gaining and one is losing. So oxidation and reduction are just opposite processes. You cannot have oxidation if you don't have reduction. Anywhere you see reduction, you have to see oxidation as well. Because if something was losing electrons, if something was giving away electrons, where do those electrons have to go? To something else. So if something is losing electrons, then something else has to be gaining electrons. And then we went over our rules for assigning oxidation numbers or oxidation states. I want to be very clear. This list is not as difficult as it might seem. Ions are just whatever the charge on the ion is, okay? Elements are 0. Hydrogen, 99% of the time, what's hydrogen? Plus 1. Because hydrogen is usually attached to something more electronegative than itself, right? Rarely do you see a metal hydride, and I doubt we will ever see it this year. Again, 99% of the time, what's oxygen? -2. The total sum of the oxidation numbers have to be equal to the charge on the entity as a whole. So if you see one of those polyatomic ions, right? Anywhere you see a polyatomic ion, you can immediately just add up all of the oxidation states, and they should add up to whatever the charge on that polyatomic ion is. I'm gonna pick a real pain in the butt, a polyatomic ion, and I want to go through it together if that's okay. What's a pain in the butt? Oxalate. Oxalate's really not that bad. Let's do hydrogen oxalate. When I say the word hydrogen oxalate, what comes to mind?
H-O-O-C-C-O-O.
H-O-O-C-C-O-O. H-O-O-C-C-O-O, right? No. Negative. That is such a huge difference. It makes such an important difference that we add that negative charge on there. So what do all of the oxidation states of all of these things have to add up to be? -1. So let's do this. Let's try and figure out what are the oxidation states of the carbons here. That's our goal. That's what we want to try and figure out. Now, how many hydrogens do we have? 1. And what is the oxidation state of a hydrogen? 1. So we've got 1, right? 1 hydrogen. Plus, how many oxygens are here? 4. So 4 groups of 2. And then how many carbons? So we got 2 carbons, and what does that all have to add up to be? -1. Just a chorus of monotone words coming at me right now. So let's add all this up. Let's simplify it. What's 4 times -2? -8. So 1 plus -8 is -7. Whoop, -1. So I'm going to add 7 and add 7. You got 2C equals 6. C equals +3. Now, that was pretty, would you agree that was on the more difficult side?
No.
I would say, as far as oxidation states go, that was on the more difficult side. It really, really sincerely was. Totally. I'm going to do something that's a little bit worse now, if that's okay. Awesome. Yeah. I'm going to ask you to look up the formula, or if you haven't memorized, write down the formula for butane. Butane. CH4 is methane. Meth is 1, F is 2, prop is 3, but is 4, right? C4H10. I want you to try and figure out what is the oxidation state of the carbons in C4H10.
Where's their special rule? Let's see here.
If you have absolutely no idea what to do, what would you start with? What's the total charge? 0, right? All of the charges have to add up to 0. All the oxidation states have to add up to 0, right? What do you know anything about either hydrogen or carbon? You know the hydrogen, so that's 10 plus 1s, right? And how many carbons are there? 4. So let's rearrange this. I'm going to subtract 10. So what does my C have to be? -5/2. -5/2. Oh, what a stupid oxidation number. Let's see why that is. Can we draw out the structure of butane? Is that okay?
Sure.
You don't know anything about butane. We haven't done organic chemistry yet. But let's do this. How many carbons are there?
4.
And how many hydrogens are there? 10. So we're going to put each carbon has to have 4 bonds. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10.
That's enough.
We want to know why is the oxidation state for carbon -5/2, or another way of thinking about it, -2.5. Well, that's because two of the carbons in butane have an oxidation state of 3, and 2 of them have an oxidation state of 2. And what's the average of 3 and 2? 2.5. Can you see how 2 of these carbons are going to have an oxidation state of 3? The carbon is more electronegative than the hydrogen, so the carbon is stealing these electrons, right? Same here, it's stealing those electrons. But what about the middle carbons? It's just stealing 2 electrons each, right? But, okay, hopefully that doesn't really freak you out, because it's, some of them are 2 and some of them are 3, so that this adds up to be, an average of 2 and 3, that kind of thing. Let's try and figure out what happens when butane burns, okay? So I'm going to erase some of this stuff. We're just going to assume that the oxidation state for butane is negative 2.5. And I'm going to write out the formula for the burning of butane. But you actually have it. It's right here. I'm going to write it out, but you have it. Which one?
G.
It's G, right? Butane, 2 butanes plus 13 oxygens gives us 8 carbon dioxides and 10 waters. C4H10 plus 13O2 gives us 8 carbon dioxides plus 10 H2Os. And I'm going to forego states of matter because I'm a lazy button. Okay, let's try this out. What is the oxidation state of the hydrogen in butane? +1. So let's write a +1. What is the oxidation state of the carbon? We just figured it out. It was -2.5 or -5/2. Whatever, doesn't matter. -2.5. Just roll with it right now. Oxygen.
Wait, no, it's 0.
Why is it 0? It's bonded to itself. So nobody's stealing any electrons, right? It's bonded to itself. What about the carbon and the oxygen in carbon dioxide? Okay, so oxygen, because it's bonded with something else, what do we know it is? It's -2. Because there's 2 -2s, how many positives do I need to balance out that? +4. We could write that out. We could be more explicit, right? The whole thing has to add up to be 0. You've got 2 -2s from the oxygen. And then we're trying to figure out what the carbon is. So if we rearrange this, carbon is +4. Okay, +4. And then what about the hydrogen and oxygen in water? -2 and +1, right? Because 2 positives cancel out 2 negatives. So let's take a look at this reaction, and I want you to tell me, is there any change in oxidation state anywhere in here? Do you see any elements that are changing their oxidation state? Max? Carbon is changing its oxidation state, right? And it doesn't matter what the change is right now, as long as we understand that it's changing. Is the carbon gaining electrons or is it losing electrons? When we go from -2.5 to +4, it must have lost electrons. I don't understand, but the oxidation state went up, right? How can it lose something if the oxidation state went up? Joe?
It loses negatives, it becomes more positive.
When you lose negatives, you have positives left over, don't you? Right? So we're losing electrons. What I want to do, I want to start getting used to this idea of the substance that's losing electrons. We're going to start drawing like a little squiggly arrow down to indicate that it's losing electrons. Well, if this thing's losing electrons, something else has to be gaining electrons. What's gaining electrons? The oxygen in the oxygen. That sounds stupid, but the oxygen in the oxygen has to be gaining electrons. So what substance in here is being reduced and what substance in here is being oxidized? Real gas. So the first one, is it losing or is it gaining?
Losing.
Losing. So is it oxidation or reduction?
Oxidation.
So this thing is being oxidized or it's undergoing oxidation. They're the same thing. If you're being oxidized, you are undergoing oxidation. If this thing's being oxidized, by default, this thing has to be reduced. Are we kind of okay with that idea? This squiggly arrow up and down is not going away anytime soon, so we'll just get used to it.
It's called oxidized because maybe like a good rule of thumb is that oxygen is zero when it's by itself, and something's always going to be different from zero. It's gonna oxygen's always going to be reduced, and the thing that's not oxygen is going to be oxidized.
I'm gonna be. Can I show you an example of when that's not the case?
Yeah.
Okay. Can I talk to you guys about an example where that's not the case? And this is me being a pretty big asshole, but we're gonna go through it together, so it doesn't really matter. Yeah. Classic Walton, just being a jerk. That's okay, let's try the reaction of oxygen gas. I don't know why I feel the need to go on my tippy toes when I write on a whiteboard, but I do. We're going to react oxygen gas with fluorine gas. So we're going to react these two things together. And when we react them together, we get this weird combination called OF2. That's a gas. Oxygen difluoride. And so, let's balance this reaction because we probably should. So where do you want to start off by balancing?
Two on the right.
Okay, so we got 2 fluorines and 2 fluorines. But we have 2 oxygens, so we need 2 oxygens. Now we have 4 fluorines, so we need 2 fluorines. Okay, that's fine. Now, let's assign some oxidation states to this reaction. What's the oxidation state for oxygen right here?
0.
0. Why is it 0? Because it's an element all by itself, it's bonded to itself, right? What's the oxidation state for fluorine here? 0. What's the oxidation state for either one of these things? Let me show you what OF2 looks like. Who's more electronegative here? The fluorine is more electronegative, right? So the fluorine's more electronegative. So the fluorine steals the electron, and the oxygen becomes +2. Whoa, man, that's crazy. You'll never see this. It's never going to happen, okay? But I need you to understand that this kind of stuff is possible. And the only reason why I bring it up is because Max asked me, something reacting with oxygen, is it always going to be oxidized, right? That was basically your question. So the fluorine, is the fluorine gaining or losing electrons? It's becoming more negative, so it's gaining electrons. And the oxygen, is it gaining or losing electrons? It's losing. So right now, what's the oxygen doing? It's getting oxidized. The oxygen is being oxidized, which is insane to kind of think about that. It's usually the oxygen that is oxidizing something else. So this is being oxidized, and this is being reduced. But that's like a crazy example. I wouldn't worry about it. It's all good. Max.
So is that only the case with things that are more top right than oxygen?
Yeah. What are all of the elements that are more electronegative than oxygen? Fluorine. And the only way that oxygen can bond with fluorine is if it is basically this style of a reaction.
Okay.
So I wouldn't worry about it. But just because you asked the question, I mean, the answer was either going to be yes, which is untrue, or no, and I had to explain why. So, hopefully that's okay. Okay, let's do one other example before I get you to do some examples of some stuff. So, methane burns in a furnace, carbon dioxide, and water for it. You already did this, didn't you?
Yep.
And I was supposed to do, and I didn't change water for it because I'm a moron. Let's try this. CH4 gas plus O2 gas. Should have already done this, so I'm going to go really quick. We should always have a balanced chemical reaction. So 1 carbon, 4 hydrogens, 4 hydrogens, and then we've got 2 and 2 makes 4, so 2. So 1, 2, 1, 2. And when I take a look at this, what's the oxidation state of the hydrogen in here? +1. That means the carbon is what? -4. The oxygen here is 0. What's the oxygen in carbon dioxide? -2, so that's +4. Max.
Why is methane, like, shouldn't that equal 0? Because it doesn't have a charge.
Yeah.
Oh, cool.
Are we good?
Yeah, I just need new glasses.
Yeah. There's 4 of them, right?
Yeah.
Yeah. Was that the only problem?
Yeah.
Yeah. Okay. So there's 4 positives and 1 -4, so that balances out. And then here, right, the only reason I'm going so fast is because you should have already done this. Oxygen is -2, hydrogen is +1. So is there anything in here that lost or gained electrons?
Both.
Both. What do you mean both?
Carbon lost.
The carbon lost some electrons and the oxygen gained some electrons. And so the carbon in methane, was it oxidized or was it reduced? It was oxidized because it lost electrons, and the oxygen was reduced because it gained electrons. This is the format I would like us to use if I give you a question. I want you to try it out. I would like you to use the squiggly up or the squiggly down to represent up, like gaining and losing electrons, because we're going to use that process a little bit later on to build off of it. Do you want to do these questions or do you want to do different questions?
Less.
Both. Less. You're so smart, thinking outside the box, Marcus. Here, I'm going to give you different work.
Which one has less?
That's okay. Which one has less? That one, but I'm not going to do that one.
No.